I'm fortunate to have lived through all this, through my preteen and teenage and 20s and so forth, on up to now. First American spacewalk at Wate in 1965. First astronauts to orbit the moon, Apollo 8 in December 1968. And a series of manned lunar landings in 1969, 1972. And then the first American space station, Skylab, in 1973, 1974, which was built using Apollo hardware. And then we had 30 years, let me go back. First robotic landing on Mars was in 1976 with Viking 1 and Viking 2. We learned a lot about Mars in that time frame. And the space shuttle flights went on from 1981 to 2011, 30 years of operations there. Space shuttle and assembly of the International Space Station. Then the Mars rovers in 2003. In 2013, Voyager 1 left the solar system, which is a landmark in space exploration that you can't match until we have something leave the galaxy, which could be a while. And then there are plans for possibly a Mars sample return in 2026, possibly using ISRU to generate either oxygen or oxygen fuel. And maybe, as Jerry and others have mentioned this morning, first humans on Mars in maybe the 2030s. So with that background, and Jerry already mentioned exactly what ISRU is, in situ resource utilization, or in plain English, getting off the land. And he gave a great analogy that Lewis and Clark had to carry everything they needed with them. They never would have left St. Louis. So they never would have gotten it. So the main reason we're interested in space resources is to reduce both the cost and the risk for NASA missions, for explicitly human missions. Now, we already use solar panels for power in space, so that's a form of in situ resource utilization, using the sunlight to generate electricity. But using chemistry and engineering, we can use even more resources that are out there, especially on planetary bodies. For example, lunar regolith contains ilmenite, as Jerry mentioned. You get oxygen out of that with hydrogen. And there are polar water, ice, and other volatiles, including carbon compounds, carbon dioxide, carbon monoxide. The moon has been considered to be very poor in terms of carbon before we knew that the volatiles were there. The L-Cross mission showed that we do have carbon sources, which is very important. And then asteroids contain regolith and metals and other volatiles, water included. And we're looking at that as a resource. And then obviously, as you heard earlier, the Martian atmosphere has water, ice, and so forth. I'll go, again, I've got some of the same charts, but that's okay. So the atmosphere is there. Curiosity, Sam analyzed that more recently, showed the water comes off at reasonable temperatures. And we know there's water available essentially anywhere on Mars. It's just a matter of concentration, either a few percent or solid water ice. And on the graphic there, the dark blue is the highest concentration, and the white or the red is the lowest concentration. But even the low is 2% water. And this is from neutron, slow neutron spectroscopy. So what does that do for you? Well, I'll go through all these reactions again, but you get a nice rocket propellant of methane and oxygen with ISP of around 360. So the current Mars Design Reference Architecture 5.0, I showed what's called a bat chart. You have one surface here and another surface up here representing the planetary body that you're going to, and everything hangs upside down like a bat from that side of the picture. The idea is to launch a surface HAB lander in year 1, land the Mars ascent vehicle on Mars after 9 months. You would produce ascent fuel for around 11 months, The crew transfer vehicle would get launched in year 2, travel anywhere 6 to 9 months, explore for a year and a half, and then transfer to the MAB and take off from Mars, go to the back to the transfer vehicle, and get back to Earth. So you're away from Earth for 2.5 years. There's precedent for long duration exploration missions on the Earth, Antarctic expeditions, things like that. This is not a totally unknown sort of thing. We can do this. People can persevere and survive these kinds of activities. And Jerry said, that using the in-situ propellant production, we can save over 25 metric tons of mass, and given that ratio of almost 10 to 1, every kilogram of mass at Mars landed, you need 10 kilograms of launch material. So that saves about 2 heavy lift launch vehicles. Yeah, it depends on which vehicle, but on that order. And if the SLS is around $1 billion to launch, they quickly save $2 billion there. So it sounds very good. So the Marco Polo project, as Jerry mentioned, some of this I've talked about last year, so it may be familiar to some of you, but I'm going to go through that quickly. That stands for the Mars Atmosphere and Regolith Collector Processor Lander Operations. And the part that I'm the lead for is the Mars Atmosphere Processing Module, or the APM. Consists of a Mars CO2 freezer subsystem and a Savatier methanation subsystem. And you already know what that does. And so I won't go into details on that. But this would also, other modules are available to deal with the soil and getting water out of the soil. The idea is to operate off of a fuel cell for 14 hours and keep a live fuel cell for 10 hours of nighttime operations. In other words, just keeping alive, not really doing much of anything. So the water we make in electrons during the day provides consumables for the fuel cell that you're operating at night. So the idea is to build something that's will operate remotely and autonomously like we want on Mars. So here's an early design of what that lander would look like. The scale is something like a small sample return mission. That is grams to a few kilograms max. This is not the larger scale numbers that Jerry talked about this morning. But there's also a power module, the soil processing module, water cleanup, light detection and drill. This is one idea. We had to have a Ames Research Center honeybee drill to analyze, drill down and sample for life. There's fuel cells for the overnight water processing module to electrolyze the water, and then the liquefaction module for the methane and oxygen liquid storage. And this would be approximately 3 meters by 3 meters in octagonal lander. So our requirements for the CO2 freezer is to get at least 88 grams an hour of carbon dioxide and provide that to the Savatier system. And you need setup purity around 99%. And we would operate using pressure similar to that on Mars. We don't have a refrigeration system to chill it down to Mars temperatures, but we're operating under the same pressure inside the freezing chamber. And let's see, here's the shape of the module that we were given. And the idea is to make close to half a kilogram of methane per day and 1.75 kilograms of oxygen a day, because the Savatier system produces water, and that's half of the oxygen we need for the system. And here's what a 3D drawing would look like. Before we actually built anything, we wanted a proof of principle that you could actually put all that hardware in the right place at the right, get it all to work together. And those are the main, just a block diagram. I won't go into details because I don't have time to go through all that. But that shows all the masses of materials moving around the system, so you know what your requirements are. And here's drawing I made of the system, we ran off of a tank of simulated Mars atmosphere over here, and we had two cryo coolers with a copper cold head on each one. One would be freezing CO2, while the other one, a batch that had been previously frozen, would be sublimating and providing the CO2 to the Savatier system. So you switch back and forth between those two. And then some storage tanks for the carbon dioxide and vacuum pump to simulate moisture pressure. And here's what it looks like after it was all built and tested. We developed a cold head here to get enough CO2. The initial tests weren't with just the standard design of a fin device that would get you the CO2. We had to come up with something better. So one of our guys, Jim Captain, worked with a thermal engineer and came up with this, I call it a Ferris wheel design. Actually, it looks more like a Mars rover wheel too now that I think about it. But here are the cryo coolers. That's a cryo cooler body there with a copper cooling coil around it. And this can is where the low pressure system is. And CO2 flows through there. And again, there's a lot more detail than I have time to go through. But there's a design of the Savatier subsystem, reactor is represented here, recycling system to take care of the excess hydrogen through using a membrane. And here's a condenser, various other valves and so forth to keep it all running. And this runs off hydrogen and CO2, or we could feed it from the CO2 freezer. So there's what it looks like after that was all put together. This is an end-on view. That's the CO2 tanks up there. And the Savatier reactor was supplied by Johnson Space Centers over there. There's a computer that operates the LabVIEW program. And there's a different angle look at it. Some valves to control the different gases. Oh, there's a cutaway drawing of what the membrane module looks like to separate the CO2 and hydrogen and send it back to the Savatier reactor and recycle to go along with that. So there's a whole thing all together. This is a chiller for the cryo coolers to keep them, take away the heat that they're pulling out of the CO2 and freezing it. And there's also a water cleanup module that was built at Kennedy Space Center. The idea is to purify the water from the soil and from the Savatier system, various membranes and so forth to accomplish that. This is a full-scale mock-up of the lander that at some point we would hope to mount those systems on and test them all together. This was done by Dan Townsend, one of our sister groups there. And to mine the regolith, they have this thing called a Razor. It's a little robot with bucket wheels on both ends. Those wheels can also be used as, in addition to mining the regolith, you can actually roll around on those if you want to. It also has a track. But the idea is you could be digging in opposite directions on both sides, so the forces of digging would cancel each other out. You don't have to have a high mass of the rover itself. So here are the results for the CO2 freezer testing. We studied it as a function of the flow of the Martian atmosphere through the system, anywhere from 0.9 to 1.4 liters a minute. We did some test stand studies that showed that it would be around this rate. And here's our 88 gram CO2 per hour freezing rate. And here's the best results. And we averaged around 100 grams an hour, so we're doing better than that. We also tested how fast it could sublimate, and we're providing it, would provide it to the Savatier, and that was also exceeding the 88 grams an hour limit. So we did real well there, and we were capturing a significant fraction, around 76% of the CO2 that was flowing through the system. So we're doing well on that. So we're very happy with those results. The Savatier reactor was a different story, unfortunately. JC, before they sent it to us, they had tested it around 30 test runs for significant amounts of time. Worked fine for them, but we couldn't make it work. I don't know what happened to it. Every time we would run it, it would overheat. So it would go over 600 degrees C, so we had to just give that up. And we would have redesigned the reactor based on SBIR project, but I can't give you the details on that. And I've essentially said that we would like to start this project up again. One of the possibilities is a master thing that Jerry talked about this morning, where we put all these devices together and operate them together for long periods of time. There's also, we also have some discussions with SpaceX about a Red Dragon mission where we can demonstrate this and possibly do a small-scale Mars sample return. And Jerry also covered what's going on with Mars ISRU, so I'll flow through that. And, this was the call for proposals, and the award was just last week, last Thursday. So unfortunately, we didn't get selected. The JSC-led team included Kennedy Space Center and some contractors. But nevertheless, the technology is going to be developed and demonstrated on Mars, and that's a good thing. So what else? Jerry mentioned Resolve, and I'll have to go through this very quickly. The idea is to go drill in a polar lunar region and examine those volatiles that come off, especially looking at what temperature does the water come off, how much energy does it take, how widely distributed is the water, is it in lenses or is it just pretty much evenly distributed? We don't really know because the orbital operations with the neutron detectors can't tell you within smaller than a kilometer in size of a pixel or something like that. And we also want to look and see what else is there besides the water. LCOS indicated that a lot of these things are there. We have to look out for hydrogen, fluoride, HCl, and mercury. Strangely enough, there's mercury there, but if you think about it, mercury is a volatile metal and move around on the moon. So Resolve has gone through 3 generations of field testing. This was in 2008. We had a Carnegie Mellon rover pulling it, and then in 2010 we had a Canadian Space Agency rover that was pulling Resolve back here in 2 pieces. And those testing, and then in 2012 we had another Artemis Junior rover from the Canadian Space Agency, and it's all on a single rover, and those all went very well. And I won't go through all the details on that, but here's some of the build-up for the 2012 demonstration. There's a gas chromatograph and a spec on board to analyze the soil. There's also a demonstration of the hydrogen reduction of regolith to generate oxygen as well. Johnson Space Center is developing that. And here's some of the people working on the system, deploying the rover and so forth. Here's an interesting diagram. This is on Mauna Kea at the 9,000-foot level. The idea is that they planted some simulated water hotspots, essentially, where the rover had a neutron spectrometer on board sticking out in front, and the idea would be to look for depression in the neutrons that were emitted by a Californian source on board the rover. Those would reflect off the water simulant. In this case, it was a plastic simulator with hydrogen in it. And so out of the 12 hotspots that were planted, they found 9 of them. They did travel a kilometer, which was one of the goals, and actually went between about 500 meters between each auger and port. So things went well there. And this goes back to how do we know, why do we think there's water on the moon in the polar regions? Well, there's neutron spectrometers showing that they're in the blue areas, high concentrations of hydrogen, and various analysis of that data. And here's a notional traverse on the moon. We would land in an area that would be sunlit for about a week or so. That is, the tilt of the planet is of the moon is such that there are some areas that would stay below 100 Kelvin, but so the water ice would still be there after billions of years. But we could get solar power, so we don't have a nuclear power source. And so I'll switch over very quickly to trash gas. The idea there is to, as Jerry said, take the spacecraft waste material generated during the flight to wherever you are on the Moon or Mars or asteroid, and convert it into something useful. The idea is to run it through some sort of reactor, oxidize it, and you can lead to making methane and oxygen out of that. So here's some of the trash that's generated is just normal human waste, packaging, clothing after it's they don't have a washer or dryer on board apparently, and so they have to throw stuff away after a while. They are working on making clothing that contains silver so that self-sterilizes. But the idea is that this generates a lot of waste over time, but we want to make it use it as a resource. And here's what actual shuttle waste looks like. They make these things they call footballs. They duct tape some waste together and use that as just a way to get rid of it in the spacecraft that visit and either burn it up or maybe take some samples back to Earth. It would be nice to use something like this for like the Morpheus lander that uses methane and oxygen. Through chemistry, you convert the CO2 and carbon monoxide with hydrogen into methane and water and make oxygen, etc. Or resistojet that you can use for thrusters. And there's an astronaut for scale, a pile of waste in there. So there's a lot of material that we can use on. Here's the Kennedy Space Center trash gas reactor that we built there. It's about 1 meter long. And there's the details of all the operations that happen there. But 4 crew members for a year would generate around two metric tons of waste. And you could get like 1.5 metric tons of methane and 2.3 metric tons of oxygen. So that's a nice process. And so I won't go through all that. There were several other things that look at. The steam reforming that was developed by Pioneer Astronautics was the best one. And so that's what we're testing at Kennedy Space Center. And so unfortunately, we're not going past this year. We hope to build something for the ISS, but we'll see what happens there. Currently, that's not planned. So hopefully one day we'll have a Marco Polo lander on Mars. The human crew will land next to it and put up a little plaque that says Marco Polo was here, and whatever year that is. And the idea is to get us to Mars. So I've got a couple minutes left for questions if there are any. Thank you for your attention. Questions? Yes.
Yeah. I know that most of the work is being done on methane production, methane and oxygen. Is there any work being done on simply taking the Mars ice directly and turning it into hydrogen and oxygen propellant? I understand that what?
Turning water into hydrogen.
Turn the water, yeah. You just simply you find a source of water that's pure enough so you don't have to worry about the soil absorbing the water. You just let it melt, you filter the water out, you turn it, you purify the water, and then you electrolyze it into hydrogen and oxygen. Yeah, what I'm interested in is the total amount of power that you need to do that per, kilogram of water or whatever.
Well, that's a known value. I don't know it off the top of my head of how much energy it takes to electrolyze the water, but it's significant.
Yeah.
In a standard Savadia electrolysis system, the majority of the power is for electrolysis of the water.
Right.
So we still have a large investment. I'm not an expert on this. My impression, Jerry's kind of answered that this morning, that the hydrogen tanks are going to be large because hydrogen is such a very low density even when you liquefy it. And so that starts adding mass to be able to have large tanks to hold it. Whereas methane, even though it's less dense than kerosene, it's still 0.4, but it's density of 0.4. So that's much, much denser than liquid hydrogen. And So, plus, vaporizing has to be kept at 20 Kelvin. So that takes a lot of energy to maintain it at a low temperature as well.
The people from Georgia Tech, with Dr. Braun, who is the former NASA chief technologist, have pointed out that having a larger, less dense vehicle actually lets you land using less propellant because you have a bigger footprint and you get better air braking. So actually the less dense hydrogen is not that large a penalty.
Well, if you're landing, yes. If you want to take off,
If you want to take off, the pressure is so low, it doesn't really, you can make a vehicle of almost any shape, and it doesn't matter when you take off.
that's not my field, so I can't really explain that. The pluses and minuses there very well.
But it seems like if you're
Yeah, last one.
okay, if you're digging regolith, it seems like you're picking up a lot of potential trace elements in the soil that could be damaging. What
I
are
didn't mean damage.
in terms, we heard earlier that there could be
the
sulfuric
HCl,
acids
HF,
and stuff like that.
H2S.
Do you think that might vary? The contaminants might vary significantly from site to site? Do we know a lot about it? What research do we need to do to reduce that risk?
Well, it's obviously more knowledge is better. So we should do some more detailed studies thither. But in general, Mars has somewhat uniform, not really uniform, but you know you're going to find silicates, you know you're going to find sulfates, et cetera, in lots of places. And the rest of it is a lot of volcanic rock. So the basic components are fairly similar. They're going to vary this way and that way from site to site. But more information as we can get at different sites. Mars rover shows information. Curiosity 2020 will tell us more and more. So we'll get there. We'll figure it out. Thank you very much.